Okay, so we're going to cover the four types of laboratory PVT tests. The first is the constant composition or constant mass expansion test. And we'll look at three different types of measurements. One for oils, and in particular oils that are a little bit lower gas-oil ratio. They're not so compressible. We could call it slightly compressible oils. Typically that would have, if you took the reservoir oil to the surface and flashed it down to stock tank conditions, you'd get somewhere around, less than around 1,000 standard cubic feet per stock tank barrel, or around 200 standard cubic meters gas per standard cubic meter of flashed oil. So for these systems, which we'll call basically slightly compressible oils, we can use a blind PVT cell. And I've made a little cartoon sketch here. There are many different types of this blind cell. But basically you have a piston pump, and that will inject some kind of call this a working fluid. The working fluid could be water, I think is what's used mostly today, or it could be, in the old days you used mercury, and you injected mercury into the cell. Today you don't use mercury in most of these PVT cells, so you have a working fluid that would be maybe water, and then that water would push a piston up and down, making the cell volume, this is the cell volume, which is the total volume. The total volume would be whatever happens to be gas and whatever happens to be oil. We don't know what's gas and we don't know what's oil because it's a blind cell. Okay, but whatever the total volume is, we would be able to measure that as a function of pressure by gauging the exact amount of liquid that's been pushed into the cell or out. So that's kind of the cartoon schematic, and you measure the pressure and you get the volume, and that's all you know. So for a slightly compressible oil, the volume change with pressure will have this discontinuity that we talked about on Tuesday. So we're now just looking at the total volume, which is the cell volume, and if we start down here at some very high pressure, this would be a pressure max in the cell that's probably going to be greater than or equal to what you think is the initial pressure in the reservoir, probably higher than that. The experiments conducted typically certainly at a constant temperature, and that temperature 98% of the time is at reservoir conditions. So that would be the reservoir temperature. And so we expand the volume, we measure the pressure, we expand the volume again, measure the pressure, and so forth, like that. And the fact that this is approximately linear is suggesting that the compressibility of that oil, which is defined as minus 1 over volume of oil and the derivative slope of that, basically, if that's a linear trend, then it's approximately a constant compressibility. Now, it won't be constant, but it'll be kind of constant. It'll probably be, the slope will start changing a little bit more as you go to lower pressures. But for the sake of argument, let's say that it looks like this. So if it stayed as a liquid, you would expect it to just stay on that trend. But then all of a sudden you get a point that looks like that, like that, like that, and like that. And if you have typically the max cell volume is typically around 4 times the initial volume that you start at. Okay, so they usually fill these cells at the highest pressure will be about 1/4 full, and then they expand it 4 times, and then they go down to some pressure. And so what we're looking for is this discontinuity. We've got this very nonlinear, highly increasing, and it's due to the gas, basically this trend here, and where it intersects this linear trend here, that's going to be approximately the best we can come up with for the bubble point. That'll be the bubble point pressure. So below that pressure, we get a little bit of gas coming out of solution. Its compressibility is probably 10 times at least the oil compressibility, so that 1 psi pressure drop gives a lot more volume increase than if it was just an oil. Okay? So if I sketch here, for example, over on the right side, what I'm going to call the kind of the total compressibility, that would simply be minus 1 over volume total, change in total volume, change in pressure. It's not really it's kind of a compressibility, but it's okay. So what it would look like is that it would look like this, slightly increasing, something like that. And then at the bubble point, there's actually a discontinuity. And then this starts going up almost as, at low enough pressures, it almost goes as 1 over pressure, because that's the gas compressibility equation. The compressibility of gas is approximately 1 over pressure. So as you get more and more gas in the system, it approaches that 1 over pressure. So there's actually a discontinuity at the bubble point, and that's why we can see this discontinuity in volume versus pressure. So that gives us the bubble point, typically within about probably anywhere from a few psi, I'll say 5 psi, to the uncertainty increases as it becomes more compressible, as this discontinuity becomes smaller, so might be as much as 150 psi. By the time it gets that big, you should not be using this kind of equipment. Sometimes they do. The early Ecofisk oil samples were conducted with this kind of equipment, even though the GOR is around 1,500 cubic feet per barrel. So there was some uncertainty in those initial bubble points of the original Ecofisk oil here in Norway, back in the late 60s, early 70s. Okay, so that's reported, and then basically we end up with a table of pressure, total volume. That total volume is not reported as a total volume in cc's. It's reported relative to the volume at the bubble point. That's the most common. Okay, so that would have to be relative to that volume. And then, because we know the amount of mass that we put into the cell, we know the mass in the cell, so that so this would be at initial pressure. That would be down at the bubble point. That value would be 1. And then this would be at lower pressures, maybe down to typically around 1,500 psi. That would be approximately 4. So here, in this range here, we would get the oil densities because we know the mass of the oil in the cell, and we know its volume, so we know the density, right? But down here, we don't know the oil density because we don't know how much is gas and how much is oil. So down here, we don't get any numbers. And that's pretty much all you get from this experiment for a traditional oil. You get the density above the bubble point, and you get this total relative volume. And of course, the bubble point pressure estimate as well. That's the first experiment.
How do they measure the mass of this pressurized oil?
How they measure what?
The mass of the oil.
Okay, how they measure the mass initially? Okay, let me just get this. When they inject the sample into the container, they either do it from separator samples and they actually know the mass separator oil they put in, the mass of separator gas they put in, or if they inject a reservoir oil sample, then they would basically know the volume they put in, and they would have to have measured independently the density. So they'd have to have an independent measure of the density to calculate the mass. Basically, because you know the molecular weight of the stuff, you know the volume that you move into the cell at a fixed pressure and temperature, and you'd have to have the density at that pressure to get the mass. So. Okay, so that's the first experiment. Let's see if I can look in chapter 6. That table should be in there. Oh, give me a break. Why doesn't it let me? Where's the thing to go down? The scroll bar. Let's see here. DLE. There we go. CCE reservoir. Okay. So this is a sample table 6.9 CCE reservoir oil, the relative volume, pressures, high pressures. This is the bubble point pressure. Okay, this Y function, I'm not going to talk too much about that. It's so basically these are the numbers. You also get a compressibility, approximate compressibility above the bubble point. You can see that it's increasing as the pressure goes from high to low, a little bit like I sketched. Specific volume, that's the inverse of density, cubic feet per pound mass. So that's, I guess I can just copy this in. Notes. Okay. So this here is basically what we call specific volume on a mass basis, so I'm not sure exactly how I would write it. That's basically the same as 1 over density, mass density. So if you took the inverse of that, it would be, 40 some pounds per cubic feet. We've got these compressibilities showing the decrease or the increase in compressibility as you approach the bubble point, and then this relative volume, this is total volume over the bubble point volume, and you've got the bubble point here. Okay, and the Y function is defined down here. Basically, we don't use the Y function anymore. Its purpose, because when they bring the system, try to bring the system to equilibrium, where the gas and oil come to equilibrium, if they don't wait long enough, don't really bring it to equilibrium, then the volume they get at that pressure really won't be kind of an equilibrium volume. So if you look in detail at particularly these volumes just below the total volumes at pressures just below the bubble point, show some scatter, and that's because of this lack of getting the equilibrium. And if you plot this y function, which really nobody much does anymore, you might show some scatter, this being at the bubble, or just below the bubble point, but then this basically will get on trend, something like that. And it's pretty much a linear trend, should go up like that. So these data that are off trend, you can correct them. Okay, but the amount of correction is not big. It's not a big deal, but because we don't usually use these data directly. In the old days, you might use those data directly in your engineering analysis. Today, we don't use them directly. So the Y factor plot is just to identify numbers, and it might just be that should be 2.7, should be 4.6, might be, it should be 5.8. Not big changes, but some changes. But it shows up very clearly on this plot. So, okay. So that's this first type of CCE data. Okay. The second type would be CCE for this would be for oils and all other gas condensates. And here we use a windowed PVT cell. And there's a number of types. I'm not going to get into that. Basically what we're doing here, again, we just charge the cell with a certain amount of mass of material, keep it at a fixed temperature. We change the pressure, and we measure the volume of oil and the volume of gas are measured, and the total volume. This would be at some high pressure greater than or equal to the initial reservoir pressure. You'd come down here to the point where you find the saturation pressure. It's either going to be a bubble point or a dew point. And then we'll go down here, and basically we'll get down to some low minimum pressure where the total volume is approximately 4 times the saturation pressure, approximately. So this is what's measured. And then what's reported is typically the total volume over the saturation volume. So that'll be 1 here. That'll be about 4 here. And then we get the oil volume in one of 2 ways presented. The most common way would be oil volume as a function of total volume, or relative to total volume, or I suppose some give both, oil volume relative to the saturation volume. We call these relative oil volume. There's 2 different types, 1 and 2. And they usually have a footnote telling you which one it is. the thing you need to remember is that the first definition is an oil volume which will vary with pressure divided by the total volume, which also varies with pressure. And the total volume at low pressures really varies a lot. Okay? There's a lot of variation. So you're getting, you're gauging the change in two volumes with pressure. The second definition is oil volume, which is a function of pressure, over a constant saturation volume. So the only thing that is gauging is how the oil volume changes. Okay? So in a sense, this is probably the preferred. Now, if they give you one and they give you this ratio of total to saturation, you can convert VRO1 is VRO2 times 1 over VRT. Okay, so you can get the VRO2 if you want it. You just divide, basically you just divide this. It's kind of a screwy way to write this, but let me okay. I think that's right. Because then the V totals cancel. Is that right? Yeah. Yeah. No, maybe. No, that's all right. See, if we multiply it by VRT, that should be right. Okay, sorry about that. And this is the one that, no, oh man. Shoot me now. Okay. We want VRO2, basically. It's a measure only of the phase amount. So if we want 2, we take 1, which is that, and then this is correct. Okay? How many ways can he get it wrong before he finally gets it right? There's a number. Okay. This is VRT. Sorry. Total relative volume. This is the VRT. So they always give this, and then they'll give one of the two relative volumes. Now, for reservoir oils, you'll also get the oil density above the bubble point. And for reservoir gases, they'll typically give you the Z factor and or the gas formation volume factor. Okay? And these will be given at and above the saturation pressure, where it's single phase. So for oils, they'll give you oil density. For gases, they'll either give you the Z factor of the gas or the BG of the gas. And that BG that they give you will be the standard BG like that. So this is all the reported data. here. Yep. So what I need to comment on is how do we establish this saturation pressure? Okay? Because this has for sure some uncertainty. Probably here at the best you're 10 psi, and it might be into the hundreds of psi. Uncertainty. That's hundreds. Okay, so we measure oil, gas, and total volume. We report this relative total volume. We report some form of the relative oil volume. And then in the single phase region above the saturation pressure, we give the oil density or the gas property.
Excuse me, is that oil or gas in the promotion point factor of gas? I mean
This one here?
TSO.
TSC.
Oh, that's what I wrote. You can't read it? Yeah. T, standard condition. It'd be 520 Rankine or 60 degrees Fahrenheit, 15.56 degrees C. This is just the standard definition of BG. Okay. They convert Z factor to BG. Why they do it, I'm not sure, but it's better to get the Z factor. But okay, now
This information volume factor, this is for the wet gas.
yeah, we haven't really got. We'll get into that when we start talking about Blackwell tables next week. So I don't want to confuse anything now. It's just this is the traditional definition. Of the gas formation volume factor. We're going to talk about this in great detail next week and the week following, so we'll get to that.
But how do they measure this FG?
Well, they basically know the mass in the cell and they know the moles in the cell because they know the molecular weight of what they put in the cell, right? So if they know the mass and the moles and the density, then they have the Z factor. So basically you have to know what the moles are in the cell initially.
But they can also do they can measure the volume of the gas in the cell, and when they flash it, they can measure the volume of that gas again.
But they don't flash it. They don't take anything out of the cell. So you basically, when you charge the cell, the lab will say, oh, we know how many grams we have of material in the cell and how many gram moles of material we have in the cell. So. Okay, so let's look at how the PSAT is determined. So basically what they do is they use a graphical plot of VO versus pressure. Okay? In both cases, for oils and gases. And I'll sketch what it should look like for oils first. So for reservoir oil, it should look something like this. We start out here. We get this increase because it's a more volatile oil. That should be a little bit higher. So you've kind of got a trend going. And then you basically get a point where it goes like that. Okay. So the oil, instead of increasing in volume, it starts shrinking. So if you kind of blow up around here, you've got a point here that's on trend. So this, you do kind of a trend analysis, and where these intersect is what you're going to call the bubble point. They don't look for the first bubble of gas, okay? Their eyes are not that good. So they're basically looking in this discontinuity in oil volume versus pressure. And of course, depending on two things, the accuracy, the plus minus, depends on mainly two things. First, it depends on how many and how close you have pressures, near by the bubble point. Okay, so if you only had this point and this point, it would be more difficult, right? More uncertainty. The more points you get close to that bubble point, the more accurate. And the second thing is to make sure that you bring all points to equilibrium. Because you can have this supersaturation effect, that if you just lower the pressure, maybe the gas doesn't come out of solution. If you shake it, the gas comes out of solution. So if you don't shake it enough, you might get partial gas out of solution. So basically, there's a requirement of physical agitation over a certain amount of time to bring the system to a true equilibrium. Okay? And if you don't do that, because time is money and labs like to make money, then some of these points may not really be where they should be. And that makes it more uncertain. This is the uncertainty. Okay, so now let's look at the reservoir gas, gas condensate. And again, we plot oil volume versus pressure. Now we start with zero oil volume, right? So we're going to have a point here. We don't see any oil. We don't see any oil. We don't see any oil. And then, because there's not very much of it, it may be hard to quantify, but they see fog or they see liquid droplets, but they can't quantify how much. Okay? So what they'll do is that they'll basically put a number, like they might put it at the 0, and they'll say that at these two pressures we saw what they call a trace. It's definitely liquid appearing, but they can't measure the amount. Okay? And then they get the first measurable amount, and then typically it'll look something like this. It'll max out, and then maybe it'll drop down, because remember, the cell volume is now expanded to 4 times, and they have to stop the experiment. So typically you'll get something looking like that. And then they have to do some kind of interpretation of where's the dew point. Okay, so these 3 points here had 0 amount of liquid. So the dew point should be less than that. But the first time they got measurable liquid was here. Okay? But somewhere in here is the first epsilon little drop of liquid, right? So somewhere in here is what they will report as the dew point. They will give it with 4 or 5 significant digits. okay, because that's the way the labs work. But they don't measure it with 4 or 5 significant digits. They measure it plus minus 10, 100 psi. 1 bar, 3, 5 bar uncertainty. Okay? And if you want to get more accurate, then you have to make more measurements, and you have to say, well, where do I find a trace out here or a 0 out here? And you can kind of close the gap a little bit. You can't get 1 psi accuracy. Okay? This curve here is what we refer to as the liquid dropout curve, because liquid is dropping out of the gas. Kind of in this range here. What do we have going on? We have retrograde condensation. Right? Because as you're lowering the pressure, the increasing amount of oil volume, and below that maximum, you have kind of a revaporization. Some of that condensed liquid is revaporized back into the gas. You don't in the laboratory do it, but if you actually, the way this would actually look, this would probably be kind of like that. If you could go that far, it would probably look something like that. And only at very low pressures, very, very low pressures that you would like put it on vacuum, which you're not going to do. With this, it won't turn down to 0. You'll never see it turn down to 0. Okay? You can use a calculation like your Excel program calculation, and what you might find is that this, you get to a low enough pressure, and this, can't even do it here. Basically, at very, very low pressure, it might start going down towards, but you're on a log scale. You're at 10 to the minus 6 psi. All the liquid disappears, the lower dew point. So realistically, this liquid volume kind of will just hang in there. It might even be flatter than that. Okay, so that's just as a comment, we're working on a field in Kazakhstan. I think it's the largest field in Kazakhstan. They have a couple of really monster fields. The Karakanajak gas condensate field. And